The universe, a vast, intricate tapestry of phenomena. But beneath its vibrant chaos, beneath the dance of stars and galaxies, there lies a relentless, invisible force. A force that dictates the very direction of time, the ultimate fate of all things. It's called entropy, and it is arguably the most fundamental law governing our reality. Often misunderstood, frequently simplified to mere disorder, entropy is far more profound. It's not just about things falling apart, but about the statistical inevitability of energy dispersal, of possibilities unfolding. In classical thermodynamics, entropy is defined as a state function. It's a measure of the energy within a closed system that's simply unavailable to do work. The second law is clear. In an isolated system, entropy can only increase, or, at best, remain constant. But this macroscopic definition, while practical, felt incomplete. It didn't explain why heat flows from hot to cold, or why an egg doesn't spontaneously reassemble itself after cracking. It took Ludwig Boltzmann in the late 19th century to bridge the macroscopic world of thermodynamics with the microscopic realm of atoms and molecules. Boltzmann revealed entropy as a measure of the number of microscopic arrangements that correspond to a given macroscopic state. He called these microstates W for Wahrscheinlichkeit, or probability. His famous equation, S equals K log W, linked entropy, S, to the natural logarithm of W, the number of microstates, multiplied by Boltzmann's constant, K. It's a statistical probability, not just a measure of visual disorder. This statistical understanding holds the key to one of physics' most elusive concepts, the arrow of time. Why does time seem to flow only forward, never backward? At the fundamental level, the laws of physics are largely time-symmetric. A billiard ball collision looks the same whether played forwards or backwards. Yet, pour cream into coffee, and you'll never see it spontaneously unmix. The irreversible nature of everyday events stems directly from entropy. It's overwhelmingly more probable for a system to evolve from a low entropy, that is, a highly ordered state, to a high entropy or disordered state. This implies a universe that began in a remarkably low entropy state, a past hypothesis that underpins our understanding of cosmic evolution. It was incredibly special. Without entropy, there would be no distinction between past and future, no memory, no causal chain. Time's relentless march is, in essence, entropy's relentless march. Think about your own life. Your experiences accumulate, memories form. You can't unlearn what you know. You can't undo a broken vase. Entropy's signature is everywhere, in every irreversible moment. Let's correct some common misconceptions. First, entropy isn't simply disorder. A perfectly crystallized diamond, a highly ordered structure, can have higher entropy than a disordered gas under certain specific conditions. Second, entropy doesn't always increase everywhere. Life itself seems to defy entropy, building complex, ordered structures, but this is only possible by exporting even greater entropy to its surroundings. Third, maximum entropy doesn't necessarily mean ultimate messiness in the visual sense. A universe at thermal equilibrium would be uniform, bland, yes, but not chaotically messy in the way we often imagine. The core idea, the true essence of high entropy, is the dispersion of energy, spreading out, becoming less concentrated, less available to do work. It's about maximizing the ways energy can be arranged. Beyond physics, entropy finds a surprising and profound parallel in information theory, pioneered by the brilliant Claude Shannon in the mid-20th century. Shannon entropy measures the unpredictability or uncertainty of information. A message with high Shannon entropy is one where each symbol is highly unpredictable, carrying maximum new information. Think of it as true surprise. This is precisely why data compression works. By identifying and removing redundant, predictable patterns, we reduce the information entropy of a file without losing essential data. Knowledge, in a sense, is the reduction of uncertainty. Gaining information means decreasing your epistemic entropy about a subject. You are making your internal system of understanding more ordered. Even black holes, those cosmic enigmas, are now understood to have an entropy proportional to their surface area, suggesting a deep connection between gravity, information, and the very fabric of space-time. Perhaps nowhere is the battle against entropy more evident, more compelling, than in the phenomenon of life itself. Living organisms build intricate, highly ordered structures. From a single cell to a complex human being, all are remarkable pockets of negentropy, temporarily defying the general cosmic trend. But this local order comes at a cost. Life is an open system, constantly taking in high-quality energy from the sun, from chemical reactions, and metabolizing it. In doing so, organisms convert this high-quality, low-entropy energy into lower-quality, high-entropy waste products, heat, carbon dioxide, metabolic waste, constantly exporting disorder to their surroundings. Evolution, too, can be seen through an entropic lens. Organisms that efficiently manage energy flow, that can maintain their internal order by exporting disorder more effectively, are those that survive and adapt. Life is a magnificent, transient triumph against the relentless tide of entropy, a temporary, localized reversal, paid for by the greater disorder it creates elsewhere. It's a fleeting spark. Now, let us turn our gaze to the grandest stage of all, the universe itself. What does entropy portend for its ultimate destiny? Our universe is expanding, carrying galaxies further apart. This expansion intrinsically increases the available volume for particles, thereby increasing entropy by spreading everything out. Stars are massive furnaces, converting hydrogen into helium, creating heavier elements, temporarily battling entropy by concentrating energy. But they too eventually die. All fires burn out. In the unimaginably distant future, stars will cease to form. Black holes will evaporate through Hawking radiation. Photons will redshift into oblivion. The engine of the cosmos will run down. The universe will reach a state of maximum entropy, often called heat death. A cold, dark, vast emptiness where all energy is uniformly distributed, with no gradients left to drive any process. No stars, no planets, no atoms perhaps. Only a diffuse soup of fundamental particles, too spread out, too cold to ever interact meaningfully again. The ultimate quiet equilibrium. This future is billions, even trillions of years away, almost incomprehensible on a human scale. But it is, according to our best understanding of physics, the universe's inexorable destination. What does this mean for us, for meaning? If all things tend towards formlessness, does our brief, vibrant struggle for order ultimately matter? Perhaps it underscores the profound value of the present moment, the vibrant, low-entropy states we inhabit, the complexity we create, the knowledge we accrue. These are fleeting, precious exceptions to the rule. Our quest for understanding, our drive to build, to create art, to connect, these are not ultimately futile gestures against an indifferent cosmos. They are our way of imbuing the universe with temporary, glorious order. Entropy. It is the universe's ultimate accountant, balancing the books of energy and probability. A relentless march to oblivion, yes, but one that makes our fleeting, improbable existence all the more wondrous, all the more meaningful, and now, perhaps, a little less mysterious.